Find the reaction force on the door, Fr, in kilonewtons. In this problem, liquid concrete with a known specific gravity is held back by a vertical door, which is positioned above a hinge, which is on top of a vertical wall segment. The door is triangular in shape, measuring 0.4 meters tall and 0.3 meters wide. We'll assume that the wall is located around the sides of the door as well, to hold back the liquid concrete. The reaction force, Fr, equals P times A, where P represents the static pressure exerted against the door by the liquid concrete, and A represents the area of the door. Also, we must recognize that the static pressure, P, is not a constant and varies with depth, in which case the reaction force, Fr, equals the integral of P times A over the entire area of the door, A. In this equation, P equals rho times G times Y, where rho represents the density of the liquid, G represents the gravitational acceleration constant, 9.81 meters per second squared, and Y represents the depth, as defined as the distance from the surface of the liquid concrete measured downward to the point of interest. The fluid density, rho, can be calculated by multiplying the density of water, rho W, by the specific gravity of the fluid. Using 1,000 kilograms per meter cubed for rho W and 2.4 for the specific gravity, the density equals 2,400 kilograms per meter cubed. The area of the door, A, equals the width of the door, W, times the height of the door, dy. Furthermore, we can define the width, W, as a function of the depth, y. From observation, we notice at a depth of 0 meters, the width equals 0 meters, and at a depth of 0.4 meters, the width equals 0.3 meters. Since the function is linear, we know the function f of y equals 0.75 times y, which makes our revised equation for the area of the door equal to 0.75 times y times dy. This makes our equation for Fr equal to the integral of rho g y 0.75 y dy. And after simplifying, Fr equals 0.75 times rho g times the integral of y squared dy. And we'll integrate from a depth of 0 meters to 0.4 meters. After integrating, we'll substitute in the limits of integration for y1 and y2. We'll also substitute in the values for the acceleration and the density. And the reaction force, Fr, equals 376.70 kilonewtons. When reviewing the possible solutions, the answer is B.